Thanks everyone for your patience, just making sure everyone could log on. And welcome to the sensor-based sorting webinar, which is a joint venture between the Saskatchewan Research Concil and TOMRA Mining, two leading organizations in the field of ore sorting. Both companies have long supported base metals projects with the adoption of sorting into their operations. And so we have developed this webinar with experience and capability over the years and are bringing it to you today. Before I just do a brief introduction, just some housekeeping rules. As you can see, there is a chat, which is obviously live to everybody. Please put any questions you have in the chat for either of the speakers or just a general question. If we don't get to all of the questions, we will endeavor to follow up. We always do that after our webinars. And we will also be sending emails of the people that are answering the questions to you if you would like to follow up on any questions at a later date. The questions will be answered by a panel of experts from TOMRA and Saskatchewan Research Concil. I will introduce the panel of experts when we get to the questions section. So for now, the topic of our webinar today is, of course, base metals. Jane has just asked me to let you know as well about the recording, that there will be a recording available on both of our websites, both the TOMRA website and the Saskatchewan Research Concil website. So we know how important base metals are to the world economy and also to meeting net zero goals. We think that ore sorting can make a significant difference to not only the overall economics of the project, but also to lowering environmental footprint, as well as cut-off grades of mineable assets. In this webinar, you will learn how to evaluate whether sorting is for you and what are the most effective ways of testing and evaluating this technology for application in your operation. Our first speaker is Harold Cline. He is the North American Sales Manager for TOMRA's mining business. Harold has over 35 years of experience in geophysics, sensor-based imaging applied to a wide variety of scientific, engineering, medical, and minerals processing applications. Harold has a BSc in geophysical engineering from the Colorado School of Mines and an MS in medical physics from the University of Colorado. He is also on the American Board of Radiology and a certified radiological physicist. Thank you, Harold. And I'll just introduce Mike McCubbing, our second speaker, so they can just follow on from each other. Mike McCubbing is a professional geoscientist and business unit manager in the Mining and Energy Division at SRC. He has 20 years of experience in pilot plant operations for minerals processing applications, including processing by dense media separation for macro diamond recovery. Mike has more recently been focused on other sensor-based sorting applications for a variety of commodities, using his experience with sorting from the diamonds operations. Mike and his team at SRC have developed a sensor-based sort test facility that will utilize their decades of experience of analytical and method development to provide independent approach to evaluation of sensor-based sorting technologies for mining companies. So Harold, without further ado.
Thank you so much, Lucinda. Just getting the presentation set up here. And hopefully everyone can see that. So as promised in the registration page, we're going to have 3 sections today and also some questions at the end. So I'll just kick off with an introduction to sensor-based sorting. Don't worry if you're new to sensor-based sorting, it will be pretty basic. We only have half an hour though, so I'm going to scoot along pretty fast. After that, Mike will follow up with some more information, and I'll try to actually lead into his presentation. And then we'll just show some quick examples of base metal sorting installations. And then again, some follow-up questions. Quickly, I just think that not a lot of people have any idea how ubiquitous sensor-based sorting is. These are numbers just for TOMRA sorting. Obviously, I don't have for other vendors, but there is something like 200 operating mining sensor-based sorting installations around the world. Quite a few more in recycling and food, obviously much bigger markets. But on the top there are just some examples. Everything that comes to your table, potatoes, fruit, candies, seeds, even processed food has usually been through a sorter just to increase the quality and to remove foreign objects. In mining, lots of experience and lots of installations in industrial minerals, diamonds, both ferrous and non-ferrous metals, and in slag. And then those things that you put in your recycling bin also get separated by sorters. Just as a basic start, there are a couple different kinds of sorting, and the kind we're talking about today is also synonymously either called ore sorting or particle-based sorting. In this type of sorting, in its most basic framework, first particles are detected by a sensor as they travel down a chute or a belt. Then there's some image processing that happens. They're classified into groups. And then separation is made of those materials in classified form. These days, they're usually separated by a pneumatic process. So a quick rundown of the types of sensors that are available. Everything from color, which is the oldest technology, some spectroscopy, the new kid on the block laser, and today we're actually going to focus on X-ray transmission. SRC will talk about some other types of sensing, but XRT is really the most commonly used for base metals, and so we're going to focus on that. Quickly, the way that a sensor-based sorter works, there's some material preparation before it gets to the sorter. So it needs to be properly sized, it needs to be properly screened. Then the material is presented to the sorter, usually after a vibrating screen, and then a chute, and it either enters a chute-based system or a belt-based system. Today, we're going to talk about a belt-based system because it's the most effective for X-ray transmission. I'm just going to point out in the lower right-hand side, you can visit the TOMRA video site, and you'll see actually a very nice 3D representation of how a sorter works. One of the most commonly asked questions is, how is the separation formed? And so I actually found this nice picture here. This is just an example of a air ejector layout. In this case, you can see there are a couple hundred air ejectors. And so as the sorter does its work, does its image processing, it actually tells the air ejectors which ones to turn on in groups for how long. It's a pretty interesting ballet to make it all work. So the theme of my presentation today is know if it's a prince before you kiss it. So unlike things like haul trucks and things like that every mine needs, when it comes to sensor-based sorting, it's not necessarily applicable to every single mine. Where it does add value, it adds an increase, a very large amount of value. But there are certain times when sensor-based sorting is probably not applicable. And so we're going to try to touch on that as we go along. So just some tasks that are good guidelines for implementing sensor-based sorting. And in my mind, the very first thing is you have to have a need for sensor-based sorting. You don't just do it because it's cool or the latest, greatest thing on the technology block. This graphic has been used in many forms, but I thought this was a nice one that I actually used from Metso Autotech. So some reasons, for example, are you might have a deposit that has a low-grade zone that you're not really able to currently process. It may be that actually you can increase your life of mine by being able to mine those low-grade zones using a sorter. Another thing that is very common is to sort close to the mine face so that you can reduce your haulage costs. Another very common usage these days is to reclaim waste dumps. It seems like these days some of the waste dumps have material that's as high as the material that's being mined, just because all the grades in all operating mines have gone down significantly. Again, we can sort out different ore types. This one here, access to additional sources of revenue, is an interesting one. A lot of times when sorting a waste dump, the sorter can help remove the sulfides that are going to generate acid drainage and make those useful as aggregates, so valuable at the mine or for sale. Also, if we can reduce the amount of waste in the feed, we can reduce the energy consumption involved in more crushing and more screening. And more grinding. Also, we can hope to reduce the water consumption and also reduce the size of fine tailings ponds by not bothering to grind up waste material. Again, just some overview that I grabbed from Metso Autotech. It's kind of a different thought process for greenfields projects versus brownfields. So for a greenfield, you really have the opportunity from the beginning to do a layout that can have smaller downstream capital costs if you can actually mine less material but has more metal content. For a brownfield projects, it's usually someplace where there's a bottleneck or some sort of a problem that is now keeping you from either making more money or just being efficient. So in that case, we're really looking for an opportunity where we can improve the current process. So I just kind of have this matrix here. Again, we have to have a need. The next section we'll talk about is what sensor is right for the application. So in this case, we need to understand the objectives that we're trying to achieve. So am I trying to actually increase the grade of the material to make it suitable to go to the mill? In which case, I'm going to be sending less material and possibly less recovery. Or am I going to actually go for an objective that has me increase the yield? And actually, I'm going to report a lower grade, but my objective may be just to return more higher grade material to the mill. If you've seen our presentations before, we kind of have this strategy matrix where we try to outline what different strategies we're going to pursue for sorting. And one that in this case for base metals, the most common is to actually target the product or the ore material directly. So we're not trying to remove waste many times. We don't have to go for associated mineralogy. And usually I'm not grading base metals. I just want to increase the grade and lower the waste content. Okay, so if we go on to finding a sensor solution that is viable for every application, it's a major decision process to choose the right one, and it's different for every deposit. So really one of the take-home messages is that for base metals, test work is really necessary, not just recommended, to make sure that we're not going to kiss a frog, but a prince. Using X-ray transmission, there are a couple of different technologies that we can apply. In one, as material goes down the belt and underneath the sensor, we're actually going to collect two X-ray images. One is a low energy channel, one's a high energy channel. We're going to do some image processing, and we're going to actually then classify all of the material that's going down the belt. Notice that it's on a rock by rock basis, which is different than bulk sorting, for which you're going to do collect data over a certain amount of time, look for a trend and make decisions. For particle sorting, we literally image every single rock and make a decision. So what's the business with the red and the blue coloring here? Just a quick, I'm not going to go into a lot of detail, but we collect two images and then we basically ratio those. So we'll have a high energy channel, a low energy channel, and there'll be a cut point in between what we call high atomic density, what we call low atomic density. And I can actually manipulate that so that I'm more selective I'm getting more waste, but I'm actually then getting a higher grade, or I can be less selective, moving it down towards the red. I'm going to actually recover more ore. It's a decision that's made during test work in association with assays. Just a quick example of what dual energy XRT image looks like. So on the left, you can see that we've just formed an X-ray image. This is made a line at a time as it goes underneath the X-ray scanner past the sensors. And you get these kind of things where you can actually see, just like an X-ray of your arm at the doctor's office, I can actually see high atomic density material, low atomic density material in between. Then if we go ahead and do the classification in the middle there, using our chosen cut point, we can now make a map on a pixel by pixel basis that shows high atomic density areas and low atomic density areas. There's another approach we can do where we actually look for inclusions, so high density inclusions inside each rock. In that case, I'm literally making a map of where I see those. So just like making a map of where you see the bone in your arm at the doctor's office. And I'm looking for places where I have a suitable amount of high density inclusions to make that what I'm going to consider a product. You can see in the lower two rows, there are no inclusions. So that's my waste rock. Quick example of what that looks like. So I take my two X-ray images and actually add those together in this approach to get a nice signal to noise ratio. And I'd map where the inclusions are. In this case, what I'm looking for is basically what area in the X-ray projection looks like it's a high inclusion. If I have a rock that has very few inclusions, I'm not going to occupy much of the rock with a high density area. Quick example of what that looks like. So in the top row would be a product. In the lower, those lower few rocks represent waste material. In this case, this is a tungsten project. It works really well, the inclusion technique for this type of deposit. Okay, once we've determined that a sensor solution is possible, okay, we can see the inclusions in the inclusion processing, or I can actually make a good classification that's going to separate my waste from my gang material. There are some important considerations that I need to have, and kind of leading into what Mike will be talking about in more detail. But one of the big things that we need is actually liberation and heterogeneity. And I think Mike is going to talk about this, but this is important to discuss, especially for base metals, where I might have a disseminated deposit. So if I look at the lower row, this is just a cartoon representing rocks that have disseminated material. They're all basically the same at this scale. This is the worst case for sensor-based sorting. So if I plot a grade recovery curve, I get something like the light blue line, which tells me that I've got to recover every single rock in order to get full recovery. This means I'm not adding any value with the sorter. The optimum case is the top row in the cartoon here, where it's perfectly separated or liberated at the scale, and I can remove the ore material from directly all of the waste material. This is the optimum case for sensor-based sorting. Don't take the image in the background too literally, but I'm trying to drive home the point that throughput in a sensor-based sorter is directly proportional to the particle size that we're sorting. Notice that sorters work in the millimeter size range, and for X-ray transmission that we're talking about, generally useful from about 6 millimeters up to, if we're lucky, 100 millimeters. There's a handy rule of thumb to keep in your back pocket. If I get the average particle size in my particle size distribution in millimeters and multiply times 1.5, It just happens to be that I'll get a good estimate of the tons per hour throughput that I can achieve in a sensor-based sorter that's a meter wide. Okay, I'm going to go through this next part pretty fast, but then I'll summarize. These are just all the things that are going to contribute to throughput. First of all, if I just make a cartoon here with big rocks versus small rocks, I just made it simple for myself, so I just assumed they had 1 gram per cubic centimeter density, both of them, calculated the volume. Remember the old 4/3 pi r cubed kind of thing? Then calculated the mass and added up the mass of the particles. You can see that if I have very large particles, it doesn't take many of them to actually get a large throughput. If I have a bunch of small particles, it's going to take me, I'm not going to achieve the same kind of throughput that I would for large particles. The other thing that is a direct influence is density. Obviously, if the rocks weigh more, I'm going to get more in my apparent tons per hour. If I just make a wider sorter, I'm able to get the throughput up. If I can crowd the belt or the chute, I can actually get a higher throughput. Again, just common sense. It's not always possible to do that with base metal applications where I need to see each rock individually. So base metals and gold are probably the lowest occupancy of any material that we're going to sort. Another way, since we're on a belt sorter, is to actually just move the belt faster. This has some limitations physically. We can basically only go so fast, but our latest generation of sorters go about 3.5 meters per second. So the temptation is always there to just sort. I want the throughput to go up, so I'm just going to sort larger rocks. This is without thinking it through, is a bad way to go, because am I really getting a good liberation if I use larger particle size? Again, really important to do test work, especially for base metals and gold, because it varies a lot from deposit to deposit. Kind of threw a lot on this slide here, but it's some important considerations for the feed to a sorter. All sorters of this type work the best when the largest to the smallest particle size range is about 3 to 1. So for instance, if my bottom size is 1 inch, it works best if the top size is about 3 inches. The reason is, first of all, if I mix the size of the particles, like the image on the bottom, I'm basically going to get a lot of collateral damage when I shoot bigger particles. I'm going to shoot lots of small particles at the same time. Also, how do I design my air ejectors at the correct size if I'm expecting large rocks and small rocks? So an important consideration is designing the crushing circuit correctly for sorting. Someone was telling me last night the way to think about it is I'm not really designing a crushing circuit. I'm designing a beneficiation circuit that's going to feed the sorter. I thought that was a good way to think about it. I really need to then have someone design the crushing circuit to maximize the material that I can sort. Screening is critical so that I can achieve this 3 to 1 ratio. I don't want a lot of fines. A lot of times high grade goes to the fines anyway, so those should just bypass the sorter. For this, a nice thing about X-ray transmission is that we don't have to do a great deal of washing. However, the real world shows up sometimes, and if it's the muddy season, sorters do not like sorting mud, and so we may have to do some extra cleaning during the nasty parts of the year. Okay, really quickly, just to review what we just went through super fast, I need to have heterogeneity and liberation at the appropriate particle size range for a sorter to work. The throughput is going to be a function of the particle size, the density, the sorter width, the belt occupancy, and the belt speed. Again, just a reminder that the optimum particle size range is 3 to 1. So we talked about objectives and strategies for sorting. I always always recommend when I talk to people to, first of all, determine what they need to accomplish, have determined what the objective is, and have a strategy to get there. It's basically one of the toughest things to do is a business case. Sometimes it's obvious, sometimes it's not. I am not going to go into detail about this, but basically it's good to do a spreadsheet like this where you actually take a look at what's the throughput going to be, what am I going to eject. In this case, we're trying to eject 50% of the material as waste. Then to do a quick rundown of the costs. Realize upfront that the cost of the sorter itself is actually a fraction of the cost of a sorting plant. We always tell people that at a minimum, the sorting plant, if it's a simple one, is 2 times the cost of the sorter. It can be as much as 5 to 7 times if you have to do a lot of structural steel, things like that. But we're always happy to help people work through the capital expenditures and operating costs. And with that, I'm going to transition to Mike, who's going to take over and talk about more aspects of test work and things like this.
Great. Thanks, Harold. Thanks everyone for joining us today. Give me a second here and I'll cue up the presentation. Okay, to continue on, a little bit of background about SRC if you aren't familiar or haven't heard of us before. So SRC is Canada's second largest research and technology organization and has worked with various factions of industry, government, and communities around the world for over 75 years. We're governed by the Research Council Act. We have an independent board of directors and accountable to the minister responsible for SRC as a province. So we do receive a portion of our funding from the government, but most of the work does come from contract research and commercial services. Just over $277 million annual revenue a couple of years ago, and over 75 years of experience, as I mentioned, and we kind of balance our success over our economic performance, and here's some of the statistics on those economic factors for our success. We are based in Saskatoon, Saskatchewan, and that's our headquarters. We do have 2 TOMRA sorters at our facility currently. We've got a 3rd arriving in 2024. But why is sensor-based sorting test work important? Like Harold had mentioned, it's an important aspect of the evaluation, and no 2 deposits are the same. And so that's where you really need to evaluate this early on in the process to know if sensor-based sorting is a viable option to incorporate into your flow sheet or bring into an existing flow sheet. And it doesn't take a lot of material to be able to make some of those determinations early on. So we've got a lot of tools at our disposal at SRC that we can start to make some of these considerations. And so we can identify the physical and mineral properties, and we'll generate quantitative data. It's not a qualitative approach. We're using statistics, and we're making decisions based on empirical evidence for a lot of the cases. So small samples, like I mentioned, as small as 1 or 2 kilograms, drill core works really well. And then we'll combine that theoretical and actual data to be able to produce some outputs that decisions can be made on. Our approach to this is really working towards a standardization in a testing methodology. So we can evaluate different ore types in a similar manner to come up with this statistical approach. So I'll be citing a few examples today from numerous different ore types with some case studies for base metals in particular. Here I've got an example of CT scanning of kimberlite ore, where you can see the individual particles inside and how they may factor into liberation or size determination. Beside this one, finely disseminated ore. This is actually a rare earth ore, bearing ore, and it has been overlain by our QEM scan, showing the modal mineralogy right on top of the sample itself. So we've broken up our testing stages into 3 stages. All the way from mineral characterization, so a scoping study, into pre-feasibility, and then stage 3 would be final feasibility, where we get into increasing sample sizes as we get through the approach, and increasing data scale as we learn more and more about the ore, and then we can focus in on what are the important factors to consider at each stage. And there may be some roadblocks, and we can make some decisions at each one of these stages to determine whether or not we want to continue on that same path or need to look at things a little bit differently as far as which sensor has been identified, or what minerals or liberation factors may be need to take into consideration. So the first step is the mineral characterization, and so we're going to focus on that. So the goal of stage 1 is to identify the target mineral assemblage and ideal particle size for sensor-based sorting. Our primary go-to for this is QEM scan, where we'll do some digital petrography of the samples of ore that have been sent in. This is a uranium ore, but you can already start to see some indications on grain size and the texture of the ore, as well as the mineral assemblages and the resulting information that comes out of that, so we can start to produce a characterization table and how that relates to what sensors may be applicable for the given mineralogy of that ore. And so we'll do sorter amenability work. So this is where sample selection becomes quite important. We need fully representative material of the mineralized ore, some barren host rock or surrounding country rock, and we'll use those as the type sections to be able to analyze these in different ways to determine the modal mineralogy of each one of those lithologies, and start to make that contrast that we need to develop for the specific sensor to be chosen. The mineral properties as they relate to sensor selection, optimal particle size will also come out of this characterization. The coarser, obviously, the better. That leads to higher throughputs and higher volumes and greater net benefits. But there may be a different factor that you may not be able to sort based on size alone, or if there's other problematic ores that you might want to be able to take out at a different size, that can be determined as well. From there, we'll do some initial sorter test work where we implement some test sheets to determine the mineralogy on the liberated ores, and then we'll send them for assay to confirm the sorter efficiency, and then that will then go into models for predictions of further bulk work as we start to do those scaled up studies. So back into, as Harold referred to it as heterogeneity, at SRC, we've flipped it a little bit, and we call it homogeneity because we're looking for homogeneous particles, and so that's how we've determined a homogeneity factor, which is a method that we use when we have small samples available to us to evaluate whether or not there's the liberation potential of that particular sample that's been provided to us, and at what size. And these can be determined from core samples as much as 20 centimeters in length, or as little as 20 centimeters in length, and we'll get a first estimate on ideal particle size. So only a few kilograms of material is necessary at this point. So 2 examples. On the left, we see some, this is a lithium ore or pegmatite. This is a representation of high homogeneity. On the right, you can see a lot more minerals present. There's quartz, muscovite, some orthoclase. Purple is representative of the spodumene, and that would be our target mineral in this case. But we can start to see grain sizes in this, and that will factor into how we prep the ore for the next stage in producing some test sheets that we feed through the sorter. Once we look at that, we'll assign it a score essentially, and so it's not a percentage, but just a number value that we'll use to make the determination on how homogeneous the particles would be and how they would then lend themselves to sorting. So if we take that the QEM scanned image and we overlay it with a grid, you can see here we have a 20 millimeter grid pattern all the way down to a 1 millimeter grid pattern. And our homogeneity factor will increase as that grid decreases because you have more homogeneous particles in a smaller setting. And we're looking for a minimum factor of about 40 to be deemed as ideal for a liberated particle assessment. So here's another QEM scan image of a copper bearing ore. So you hear the mineralization is primarily chalcocite with minor bornite and azurite and as a secondary alteration product. The background here is primarily quartz and some additional calcite grains here in blue. So already we can already start to tell what are going to be the factors for liberation. Are we going to get individual particles presented into the sorter, and then what those minerals are and what those mineral properties might be to make sure that we're selecting the right sensor for the given mineralogy. So we'll jump into a case study of a gold, and silver bearing ore. And one of the deliverables from our stage 1 is this characterization table. So we'll take that QEM scan data, all the modal mineralogy that's provided, the chemical formulas, its modal percentage in that particular sample, and the average size range of the particles in that sample as well. And then we've got our molecular weight, specific gravity, atomic density, color, luster, transparency, luminescence, and magnetic susceptibility, which can all be characteristics that you could relate to the sensor type that you're going to apply. So you can start to see contrasts in the atomic density. A lot of your ore-bearing minerals are a higher atomic density. And so that will be used for the evaluation of the next stage of testing. Another benefit of going with this route of test work is you can also identify some of the problematic ores. So here we've got 2 arsenic-bearing ores in the waste material, and again, their inherent properties. And then maybe there's an opportunity that we can use sensor-based sorting to remove these earlier in the process, which can have obviously downstream effect, as Harold had mentioned earlier. So at the end of the day, we've got the characterization table and the mineral name. Atomic density would likely lend itself best, so XRT sorting for this particular sample. Specific gravity and color may also be something worth looking further into, but transparency, luminescence, and magnetic susceptibility would likely not be something that we would pursue for further test work. So arsenic-bearing minerals could be problematic if they aren't removed. Again, color could be possible. Dense media separation, you probably have a minimal return. And so this is where we're going to focus in on XRT. That likely would be the most feasible for downstream scaled up test work. So at that point, we can make a decision. What is that target mineral? What type of sorting? And what are the sizes of the grains that we need to have liberated to present that highest contrast for that sorting application? So based on sensor responses and that homogeneity factor and the size tables of each mineral will go into that decision making. And then we'll scale up. Now we're into tens of kilograms to thousands of kilograms of material. Again, representation is important to ensure that you've got all the different ore types or lithologies represented in this test work, and we can start to produce signals from the sorter itself and see how that translates from the characterization work that we've done earlier on. And so this will give us a pre-feasibility level assessment. We'll be able to evaluate the sorting efficiency based on that identified technology. And then from that, we'll start piecing together a semi-empirical model that we can use to build flow sheets and test different scenarios as far as feed rates, throughputs, grade cutoffs, and it really becomes a powerful decision-making tool on what the objectives are and how we define them as the test work scales up. Again, this can be small but representative amounts of data. We'll gather them from first inspection tests as well as some characterization results. And we're going to use the actual sorter that would be used in a field level production setting for doing this test work at this stage. So here's a bit of an example of a lead zinc deposit. So it's a carbonate hosted lead zinc deposit, dolomitic alteration and sulfide mineral zonation, ore bearing minerals, sphalerite, galena, and some minor marcasite. The samples that were provided, we've got examples of high grade ore, medium grade ore, some low grade ore, and some of the barren dolomite. And so we'll take that characterization table that we've developed from that, and we'll say, okay, well, let's assess color calibration. We'll look at the red, green, blue color saturation from those particular particles. We can classify over 30,000 color categories and color thresholds, and we'll use both sides of the rock and we'll scan them, and that data will be translated into a model to decide. You know, if you have numerous various shades of gray, it may not provide enough contrast to get a good, accurate representation. So we can test that, but it's looking like XRT calibration inspection test would be a better suited. So here we have the XRT inspection tests. This is, again, an example of the raw X-ray image. Again, here's our high grade, medium grade, low grade, and barren ore examples, all in the single test sheet. It's about a 50 millimeter particle size. And right away, we can already start to see some good contrast in those minerals. The barren material is showing mostly low density material. And as we get into the higher grade ore, you can start to see a higher density signal starting to come through. In addition to that, we'll also look at inclusion detection. And so here's the test image from the same ore particles, and you can see that inclusions are present in all of the ore types that we're testing. So that may not be relevant as we're evaluating what type of sensor we're going to be looking at. This is likely more of a finely disseminated ore and not hosted with or not related to the inclusions themselves. We can overlay that just to confirm. So now we've got the low density in red, the high density in blue, and the inclusions overlaid in purple. And so these red and purple particles with the inclusions showing through, we're not going to focus on those, and we want to make sure that we're capturing anything that has a high density signal. So again, just to bring it all together, the raw image, the raw ore, the classified images, and the high grade ore as an example here, and then the barren material on the right. Definitely a good contrast between those two. So once we've got that calibrated, and we're going to look at the sorting based on the atomic density and that high and low density contrast, we'll then transition into some cascading XRT tests. And so now we're looking for tens to hundreds of kilograms of each one of those lithologies. And we'll start to do a matrix test work on that at varying threshold settings. And so we'll adjust those for each run, and we'll establish that data set. For each one of those splits, we'll take subsamples of the resulting split from that particular threshold, and we'll submit them for assay on site to ensure that we're capturing all of the ore-bearing material in the fraction that we're expecting to see that. And then back to the images that Harold had brought up earlier, that we want to make sure that we're representing that disseminated ore. So obviously 5, we've got even dissemination. As we transition up into 1 and 2, where we're seeing more highly disseminated ore, which is going to be ideal. But we'll be able to test that. So if you have all of these black circles as ore-bearing particles, how do we remove just the white circles? And then how does that translate into a recovery efficiency based on that given threshold that you're setting up the sorter as? So the resulting output of that will look something like this. So this is a real example of a lead zinc ore that we'd looked at before, and that resulting yield versus recovery curve. And so what this represents is at a 60% threshold, we're retaining 100% of the recovery of the mineralized ore. That translates into roughly 40% removal of any non-mineralized ore, and that's all supported by assays that we've done on those resulting splits as we've tested each one of those recovery thresholds based on that particle dissemination and proportion of high to low density in each particle. So the deliverable from stage 2 is going to be a model. And so here's our lead zinc ore on a 50 millimeter feed particle, a grade cutoff. Here's the test work that we've done, some of the sorting efficiencies and the accept and rejects. You can adjust some of these parameters to start getting a better idea. As we feed more and more particles in, this becomes more robust, and you can use that to start making better decisions on how you scale up the test work and how many sorters might be required if you achieve a certain feed rate. So that stage 2 decision, again, what are the optimal mass pulls and grade cutoffs? We'll adjust that design criteria. We'll refine the model for that scaled test work, and that will take us into the 3rd phase. Phase 3 is a feasibility stage test work where we're going into full pilot scale testing. We've established the optimal yields, recovery curves. We've had conversations about what the objectives are, and we've got a clear definition of how we're going to test the sorter performance. So now this will be large volume based test work, thousands to tens of thousands of material, kilograms of material, and we're going to verify the equipment specifications, the sorter performance. We're going to look at maximizing that throughput and determine that overall efficiency against those ideal sorting parameters that we've established in the stage 2 test work. What this will allow us to do is optimize that flow sheet and implement sorting into that design criteria. So getting towards a summary, some of the key points is that mineral characterization can provide those first indications of sortability and the potential sensors. The standardized test work that we're coming up with, combined with the assays, can be used to develop those empirical models, which can be valuable tools in doing some assessment work. And the scaled testing can provide validation of the equipment for incorporation into flow sheets design. We're providing all this as quantitative data sets, and then that will translate into the modeling being used for feasibility studies and compliance reports, for example, in NI 43-101 in Canada. And some of the advantages that we've got at SRC, we are independent. We do work directly with mining companies, equipment suppliers, and contractors. We do have on-site analysis at our geoanalytical laboratories, and that includes assays, microanalysis, CT scanning, magnetic susceptibility, UV testing, and we do have full-scale pilot processing facilities as well, which includes crushing, sizing, heavy liquid separation, dense media separation, and Benson pilot scale hydrometallurgy. So even if sorting isn't the ideal solution, we can start to incorporate a full design of that test work program to look at downstream opportunities as well. So again, just a summary of the test work stages. And at that, I'm going to hand it back over to Harold.
And the objective of the next section here is to actually provide some actual base metals examples. A lot of it will be reference information for you because we won't have time to go through all of these. So just some examples of the types of educational videos that are on that website there. Please feel free to browse through there. Just back to our theme again. As Mike presented, it's really good to spend the time to make sure that you're kissing a prince, not a frog. Here's just a brutally simple example. On the left, we have a frog, and on the right, we have a prince. So this is all split drill core, as you can see. If we take an image of the deposit on the left, we can see that X-ray transmission sorting is completely unsuitable for this deposit because there's not enough contrast between ore and waste. So at this point, we would ask everyone to save a lot of time and money and not pursue this type of sorting, or go to SRC and see if there's another sensor that could be more suitable. However, on the right-hand side, we have a polymetallic deposit, and the sorter actually completely agrees with what the geologist has provided as a highly biased sample. So on the top row, we have high-grade ore. The next row, we have medium-grade ore, then low-grade ore, and you can see at the bottom is just waste material. So this would be one of the initial tests that we would do to determine whether we should continue on with this project, especially using XRT. So I'm going to quickly go through these. I'm not going to go in a lot of detail because you'll get the presentation afterwards, but just some examples again of what a lead zinc deposit would look like. So again, it would be galena, valerite, those types of things. So with dual energy, you can see a rock that's a product, clearly a lot of sulfides there that are causing a lot of attenuation. Also, we can use the inclusion method or use both of them together. A nice piece of waste on the bottom that shows there's no sulfides there. Again, this is a perfect case for X-ray transmission. It's not a bunch of disseminated sulfides that are small particles that are everywhere. I actually have some nice heterogeneity and seems like it's a good approach. Again, I'm not going to go through these, but I'm providing some examples here of test results where it has worked well. I think that Mike mentioned that Mississippi Valley type deposit, that's a great one for sorting. The carbonates have a really nice contrast with the high density sulfides. Again, now some copper sulfides. Really good example of where we have high density material that you can even see in the X-ray image. Again, dual energy and inclusion processing would work pretty well for this. Assays would be needed to make sure that we're chasing the right thing. But this is a great example. And again, I'm providing test work from several projects that we've done that show some pretty decent results. And so I'll let you peruse those at your leisure. In this case, some run-of-mine material. Sorry, the last was from low-grade stockpiles. Here's some run-of-mine copper ore. Again, it's a case where it's worked well, and you can kind of gauge whether your project is going to fit into the same kind of approach. Quickly to go through some examples. This one's been around for a long time. It's a tungsten deposit in Austria. There are actually several things that are published. On the bottom here, there's a video on our video site that tells the story pretty well. But the problem is that this mine's been in operation since 1976, And even though the head grade started at about 0.7%, these days it's down at about 0.2 or lower. And so the sorter is used to actually increase the grade that's going to go to the mill. A nice byproduct is that at a coarse particle size, they sell their waste product as road aggregate, which helps them because they have limited space for new fine tailings ponds and things like that. There is a published article. You can look that up when you get this presentation here. This is a project from Tasmania where we're using both XRT and EM sorting. This is this is a great real world example. So their task was to increase their cash flow by 20% because they needed to increase the tin production. However, as they thought it through, they realized that the mill capacity was only 750,000 tons per year. So in order to get the tonnage down and increase the grade, they actually used sorting to increase the grade of material and not bother to mill the low grade. Problem was that the sorter waste had the acid forming component, and in this case they were able to use EM to remove those acid forming rocks and then put those back underground because they had limited space to store those above ground. I'm providing a reference to this paper, which I think is actually one of the best case studies around about sorting. The reason is that they don't sugarcoat it. They basically tell the real story about we tried this, but it didn't accomplish our objectives, so we went this way. I highly recommend having a read of this article. Another deposit down in Peru, it's a polymetallic deposit using X-ray transmission notice in a container. In this case, it's veins, and so they have nice heterogeneity, and they're able to get a nice liberation. The mineralogy is all contained in veins. It's a very nice application for sensor-based sorting. This project at very high altitude in Peru is tin. It's the San Rafael mine, and you can read later about their story. It's actually got some published articles, but basically they had some goals that they needed to achieve. So they needed to treat marginal grade waste dumps, and also they had some low grade material from underground that they wanted to actually be able to mill and use as profit. So they wanted to separate this sub-economic material before it entered the wet processing plant. They wanted to also avoid the bottlenecks that were caused by the current feed rate that had too much waste in it. They wanted to improve the productivity. Again, I'm saying the same thing, by increasing the feed grade and the overall recovery. This actually allowed them to work at a lower total cash cost for every ton that they produced. They also were able to decrease the cutoff grade, resulting in a longer mine life. This is a published article. I present it as is. We were given permission to use it from Oz Minerals, a BHP company. It's a great case study. You can actually find it online, but I'm just going to take some pieces from it. So it's a mine located in Brazil. You can read the background here, but they wanted to pre-concentrate the ore because they could reduce their mine costs, be more efficient, also reduce the hauling and transportation costs. This is not on purpose, but actually their paper kind of mimics what we talked about in the last presentation. So first of all, they've determined their business case and the objectives. So from the low-grade waste piles they want to get 90% copper recovery by removing 40% of the mass. So the grade in these waste piles is less than 0.3%. Just presenting this again to remind you that we take two images. We have a cut point between what we call high atomic density and low atomic density. Again, we can manipulate that cut point to make a classification image. So here's some quick examples. This again is another case where what the geologist has pointed out to us is mimicked directly into what we see in the X-ray images. So on the left, high-grade material, high-density material. In the middle, mid-grade, and on the right, gangue material. Here's some typical results. The feed material, the copper content is the blue bars, fairly consistent. They did test work at multiple different size ranges. This particular one I pulled out, 19 to 32 millimeters. So after sorting, the concentrate from the sorter up around 3%, and the waste grade below 0.3%. Okay, I don't think we have enough time, so I'm not going to go into a lot of detail, but it's a great example. They ended up choosing one of our X-ray sorters that's actually a bigger, badder, newer model. They were able to get some throughputs at different particle size ranges up to about 150 metric tons per hour. So once they did the test work that we're showing here, they actually decided to go another step before they kissed the frog, and they put together a pilot plant to do some extensive pilot plant testing. Just a quick picture of what that looked like and their layout. And so over many days and many samples, they actually collected data from day to day and were able to show that the output from the sorter was fairly consistent. They achieved recoveries greater than 90%. The waste from the sorter, as their objective, was able to achieve less than 0.3%, and they reduced the mass that went to the mill by 40%. So pretty close to on time. And I think we have time for maybe a couple questions, Lucinda.
Yes, we do. Thank you, Harold. I appreciate you getting through that. So we do have a panel here, as Harold mentioned. I have taken some questions that you sent with registration, and I've also taken the questions that have appeared in the chat. I've tried to group them into similar types of questions. And we will be joined in this session by three of our senior scientists at SRC, Dr. Stephen Creighton, Jane Danoczi, and Zachary Lang, all who, to various degrees, work with our sorting center, and so in different areas. And so I will help to just direct some of the questions, but please feel free, Harold, Mike, Steve, Jane, and Zach, to jump in after I have directed a question. With that, away we go. So the first question I had was on uranium sorting. Harold, so two questions essentially. Just maybe you can talk about TOMRA and uranium sorting, and then about the grade ranges and the percentages that have a reliable sensor. Harold, you're free to comment on that, and then I thought Jane could comment after you.
Okay, so it's a short answer from me. TOMRA does actually not undertake uranium sorting projects. Sorry to say that, but it's a decision that was made by our stockholders, so we need to abide by that.
Thanks, Harold. So Jane, I know you and Steve have done some work on sorting. Do you have anything to say about the grade ranges that are successful in the sensor reliability?
Okay, so I'll start, Stephen. So the grade ranges that I have been aware of, I have used an M17 sorter in the past, which is a typical uranium sorter, but it was actually for low-grade material. The big issue is that once you've upgraded your material, then safety issues regarding handling of high-grade ore becomes an issue. So you've got to be really, in the lower grades to actually be able to manage it and handle it. So I've only had experience with the low-grade material. And regarding the sensors that we use in the lab, we do measure high-grade uranium, but they are reliable. And all I can think of that with the radiometric sorters, if you get your timing wrong, and this is where it will be for any ore type, if you get your timing wrong, then you're not going to get consistent results, because it's going to eject the wrong particles each time you process a sample. So they're my comments.
Thanks, Jane. That's great. Steve, do you want to add anything?
I don't think there's much to add. We have done gamma testing up with samples up to, well, pure uraninite, and we're able to detect it quite easily. Usually when you get into the higher grade uranium, the intrinsic gamma signal is very strong, and often you have to add shielding to the sensors, which are normally built for low grade detection.
Okay, thanks. And if you have, I think it was Jared that asked the question, if you have any other questions, we'll provide emails that you can elaborate on that. Then there were two questions about best practices and methodologies. Harold, I'll send this to you first. Best practices and methodologies for processing the ore before it goes through the sorter.
Okay, Peter.
Sorry, I assume that means things like preparation, moisture content. If the person who asked that question can maybe elaborate in the chat. But there was another question that was related. That person is interested in typical material handling arrangements for ore sorting, both chute and conveyor types. So Harold, I'll let you take that first, and then see if anyone wants to answer.
Yeah, I'm so sorry, Lucinda, but someone was kicking me out of this room while you were talking.
Oh,
could you please repeat the
Oh, I'm sorry. So the best practices and methodologies for processing the ore before it goes through the sorter. They didn't elaborate, but I'm assuming it's things like how do you prepare the ore, or is there,
right.
And interested in typical material handling arrangements for ore sorting, both chute and conveyor types. So I'll let you answer that, Harold, and then anyone from SRC, feel free to back up.
Sure. I'm not sure that there is such a thing as typical. I've seen so many variations from site to site. Basically, the answer is whatever works for you, but there are some important recommendations having to do with the crusher. Obviously, it's good to get somebody to simulate the crusher who knows what they're doing, but you want to optimize the amount of material that's the correct size to go to the sorter. So not having the jaws set too tight so you're not making a bunch of fines, things like that. If the material itself is very friable and it's going to just break down no matter what, you might want to evaluate whether this type of sorting is really the right way to go. A lot of times the high grade goes to the fine materials anyway, and if you're just getting a free score by all the high grade going to the fines, then that's great. No need for sorting. But there are some real benefits to also screening properly. And we always recommend screening directly before the sorter. The reason being that you can generate fines by having high drop heights or things in a hopper that are going to grind against each other. And after you've already screened it, you're just defeating yourself by generating more fines. So really having the screen right before the sorter is the way to go. Also having a highly inclined screen is maybe not the right way to go. We usually go with a low slope on the screen to get rid of as many fines as possible. But obviously you want someone who knows what they're doing to plan the residence time of the material on the screen, that kind of thing. Then really the materials handling before and after, it's good to really need to have a way to monitor the feed rate going into the sorter, because the sorter is just going to try to sort everything that you send to it. So having a variable speed drive where you can not overcrowd the sorter, you want to have a nice monolayer of material to image as much as possible.
And you already mentioned the 3-to-1 size ratios in your presentation. Mike and Zach, do you have anything to, sorry, Harold?
I was just going to say, in the real world, it never works out exactly that way, but that's a good goal to have.
I wondered if Mike or Zach, you had any from your piloting experience, any thoughts on material handling arrangements?
I think you go, Mike.
Oh, I was just going to bring up, wet versus dry processing. You can sort wet and dry ore. Usually on the coarser end, dewatered ore is fine, but as you get below 10 millimeters, even below 6 millimeters, the more moisture, you can have particles clumping, and that can affect the sortability of the ore too. But that all has to be taken into consideration with testing and the sizes that you're looking to sort.
Good point.
Thanks, Mike. Zach, did you want to add anything before we move on?
No, I think you got it. Like it really goes back to what Harold was saying earlier about like the different stages of the sorter. Like you got to be able to prepare the material, then present the material, then detect it, and then process it, and then eject it. So you need to make sure the material is suitable for all those steps, and that includes moisture and size and fines and all those things.
Thanks. That's a good way of putting it. Okay, so while we're talking about this, there was a question on what's the smallest particle size that machines can handle. This is a question I know everyone gets a lot. Harold and Zach, did you want to tackle that? Maybe Harold first.
Sure. So the very first thing to remember that we said that throughput is directly proportional to the particle size. So you always want to sort the largest particle that you can and still get a useful separation. I know that we're geeks about this, but at TOMRA, we've developed some new air ejectors that allow us to go down to 6 millimeters with base metal type ores. But you have to remember that your throughput is going to go down proportionally. So if you're sorting something that small, your throughput is going to be smaller. But if you're getting a great recovery, great upgrade of the material, maybe economically it makes sense. We build different size sorters, different size ejectors for different size materials. On the low end, really, it's 6 millimeters. The other good thing about these small valves is they use considerably less air from the air compressor. So it's a significant OpEx savings there. For other types of materials, we can go lower. For diamonds, we go down to a couple millimeters. For some industrial minerals, we're grading products, maybe making a food grade product. We can go down to 1 or 2 millimeters.
So it sounds like it's an economic as well as a technical question.
Absolutely.
Zach or Mike, of course, did you want to comment on that?
Yeah, similar to what Harold said, it's really a consideration on like how much material are you ejecting, how well can you detect your mineral. I mean, the smaller it is, the more liberated it's going to be, but you also have to be able to keep up with processing, like being able to identify and then process like in the actual brain of the sorter to eject it. So that could be a really limiting factor. You got to look at more material, and then you're going to have to be able to potentially like eject enough material too. So like the less material you're ejecting diamonds, it makes it easier. So that's why it's easier to have like go down to small sizes in diamonds because you're just there's less material to be ejected out. Maybe 1% is coming out. So it's a lot easier to do that. And like Harold said too, the feeder mechanism also has to keep up with it. Like I know air ejectors can go down to 1 mil, but some X-ray luminescent diamond sorters also have like a paddle style, which makes it a little bit easier to detect those smaller particles, but then you're taking bigger yield. So it's really a consideration of like that throughput, which he's talking about, based on size, but then also the compounding factor. If you need to have a smaller size ratio, and then you need to be able to have like a different setup to detect small particles accurately, because that can get more difficult in smaller size ranges. So you need to be able to address all those things to be able to actually like make it work for the economics of your deposit. So it's not just about how low you can go, it's how low you can go economically.
Yeah, it sounds like a lot with sorting. It depends, and so you have to test. You have to do testing. Mike, did you want to add anything before I moved on?
Yeah, maybe just one more general comment on just in sorting, because mining applications are just emerging. There's still a lot of technology to apply to sorting in general, and as we start to see more examples of mining applications, we'll learn more about the limitations of sorting in mining applications and how that would drive improvement, and how we then need to set up or come up with different ways of addressing those challenges of throughput or particle size. As we know, technology changes constantly, and so some of those things may not be achievable now, but that doesn't mean that they won't be achievable down the road.
That's a good point, Mike. Yes, things change very fast in sorting. That's absolutely true. Okay, so moving on to the next question. Someone asked about copper sulfide and copper oxide sorting. I assume the question is, does sorting work for either of these? Or is there a preferred one? And I think I can probably lead Harold and Mike, maybe you can take this, that sorting can that sorting can work on anything depending on the mineralogy. So Harold, do you want to start with copper sulfide versus copper oxide?
So copper sulfide is definitely X-ray transmission type application. There are usually other sulfides associated. We can't really tell the difference between them, but the difference between a sulfide mineral and gangue rock is usually a nice contrast. So that works well. We have taken a look at some copper oxides, and if there is a nice color, like they're usually kind of a greenish kind of color, and if it's a consistent kind of thing, and it's a useful economic kind of a separation, it's worth taking a look at color.
Okay, thanks. Mike, any comments on that?
Not too much. I guess that's just the beauty of doing test work, is to evaluate all the options, and that's something that we can certainly provide.
Anyone else from SRC want to comment on that? No. Okay. Harold, I guess the next two questions are for you. So, any successful applications in PGMs?
We have done some PGM projects. It seems like if they're super complicated, then it will work on one part of the deposit in one zone, but not consistently in another. Sometimes it's as straightforward as a color sort. And if that's the case, that's beautiful, inexpensive kind of thing. But we've said this about 500 times now, but testing is critical. But I really suggest that sampling does a lot of variability around the deposit. I think that's pretty critical, both for gold, base metals, and PGMs.
Thanks, Harold. That's a great segue into the next couple of questions, which are about mineral characterization and geomet testing. So, Steve, this one's for you. For mineral characterization work, how many samples do you typically evaluate, and how can you ensure that the samples are representative? There's an add-on question to that. What's the smallest amount that you need for analysis? So how many samples do you typically evaluate? How can you ensure representativity? And what's the smallest amount you need for analysis?
Representativity is always the hard question.
Yes.
There's no real way to guarantee representativity. So we do the best we can to cover all types of rocks that may be present in a deposit. So we would request, at a minimum, samples from a high grade, a low grade or middling area, and something that's completely barren. That way we can evaluate the mineralogical differences, see if there are any color differences, and see what minerals in each type of rock responds to what type of sensor, and what sensor-based sorting methods might be suitable for that specific type of sorting application, whether it's upgrading the ore or just removing the waste material. Sample size.
Thanks. Yes.
That's harder. It really depends on the coarseness of the mineralogy. For pegmatite, we want to get as big a sample as we possibly can. What we ideally want to see is all of the minerals in context, so we can evaluate the texture in addition to just the mineralogy, because the texture will dictate how homogeneous the material is, and homogeneity is directly influencing sortability. So
it sounds like the coarsest possible, and as many lithologies as there are present, as representative as geologists, and we would work with clients, I guess, to determine that. Thanks. So I just want to quickly I'll squeeze in two questions. Jane, quickly for laser sorting, and then I'll get to geomet testing. Is there a metric to assess the quality of diffraction to optimize sorting quartz materials? Harold suggested another webinar on this. That's a good idea, Harold. But Jane, do you have any comments on that? And what would it be the quality of the reflectivity in laser light?
Okay, I'm going to say, yes, we definitely need a webinar on this. And I don't know if one's coming up, but I'm going to go back with testing. It's when you do the measurements, because it does depend on the crystal size of the quartz. So where it is located, because quartz is everywhere in your crystal rock. So it's actually doing the measurements, seeing what you need to reject, and actually from the test work, deciding what your cut point would be.
So is there a metric, Jane, to measure the quality of diffraction? Or is it a visual based case by case basis?
It's usually well, I'm going to say a case by case basis. We actually measure the extent of the refraction or diffraction, and then and that is based on the mineralogy, and it is a case by case.
But it's a visual that you measure, right?
Okay, when you say visual to the camera might not be to you.
Yes. No, I think the question is there a metric? So is there a way, how do you determine whether there is diffraction? So yeah, it sounds like we need another webinar. Jane has got a lot of expertise on laser sorting, and we can show you how we measure that. And I know Harold has suggested that. So quickly, last question. The question that came through the registration is, I'm particularly interested in the geomet testing to assess the merits of sorting. And then there was a follow-up question in the chat. What suggestions do you have for those operators who may wish to incorporate some sort of relatively inexpensive sorting suitability metric into the geomet programs? By geomet, I assume you mean sort of grade, leachability, those types of parameters in your mine planning. I don't know, Stephen, Jane, do you want to take that from SRC side? And Harold, please feel free to chime in if you need to.
Yeah, I can take a stab at that one. So it's difficult to parameterize sortability in a single number. I think the closest thing we've come to so far is the development of a homogeneity factor, wherein we account for the number of minerals present in a sample and roughly their texture and interrelationship. So that would be the quickest way to assess whether something is sortable numerically. That's an area of active research. I think there's a lot of room for development into how we can identify sortability as a single parameter. At present, right now, it's more of an extensive set of tests that includes the mineralogy, the texture, all of the testing that we have been talking about for pretty much the whole webinar. So unfortunately, there is no really easy answer yet, but maybe Jane can come up with something in the next few years.
So we've talked to some people. Obviously, it's a dream. Sorry, Jane. It's a dream to just put in your block model some sort of sortability factor. Then as you're mining through the model, you can say, oh, this stuff's going to go to the sorter. Don't bother sorting this. It's already high grade kind of thing. That's a dream. We've worked with some people on it, but honestly, someone should fund a PhD on that because it would be super useful activity. Sorry, Jane.
Yeah.
No, thanks, Harold.
So, yeah, I was just going to add.
Okay. Got 30 seconds, Jane.
I just want to add there is a difference between upgrading and liberation, and we often get them confused. So the geometric at the front, you need to do the upgrading where you're looking at the larger samples, removing, and then later on you can start concentrating or looking at sorting for finer particles.
Thanks, Jane. Thanks so much. So Ignacio, I think Harold said he would get back to you directly on your question about the low-grade copper, and I think that's most of the questions that we sent. If you have any additional questions, please, we will provide our emails, and we're very happy to answer any and all of them. and we're 2 minutes over, so I thank everybody for joining this webinar. To Harold and Mike, such excellent presentations as usual. Jane, Stephen, Zach, thank you for being on the panel. And to Device, thank you for being the brains behind setting this up. We really appreciate it.
Thanks, everybody.
Thanks, everyone.